Hello and welcome to the fundamentals of power electronics. So last time we discussed several properties of the semiconductors, and in particular we focused on the silicon carbide and gallium nitride semiconductors. We did some calculations and we tried to obtain certain parameters, important parameters which characterize the behavior of these semiconductors, namely the built-in potential, or the contact potential as it is called, the maximum field that you can apply, and yet the semiconductor doesn't get destroyed. And third was the depletion width, that if you just put these semiconductors in PN configuration, then what kind of natural depletion width they form, the natural one that is formed because of the coming together of the PNN type of materials. We have seen that. Now we are ready to go to the actual devices, power devices, namely the power diodes, the power BJTs and so on. But before I do that, I will just very quickly summarize to you some of the properties of the various types of semiconductors that we have done, the silicon carbide and the gallium nitride. So I will just very quickly first I want to remind you that we have seen last time that both gallium nitride and silicon carbide semiconductors, they have a tetrahedral structure, and as far as the unit cell is concerned, but as far as the crystal structure, the total structure is concerned, we have seen that the gallium nitride could actually exist as a hexagonal or a cubic structure semiconductor, and similarly the silicon carbide also we have seen that it can also exist as a cubic structure or a hexagonal structure. And we have seen that in gallium nitride there were two types, the wurtzite and the zinc blende, while in the silicon carbide we had the 6H, 4H and the 3C versions of the silicon carbide, and we have seen their advantages and so on. And our conclusion is that they are fairly promising. Silicon carbide and the gallium nitride are fairly promising. So let us just summarize very broadly with whatever we have understood so far the three types of semiconductors. So silicon carbide and gallium nitride. So we are just doing as I promised with you, we are just doing a qualitative comparison of these three types of semiconductors. We tried to do a quantitative comparison last time by putting some numbers, doing some calculations, but we still have to do some more before we will be able to consolidate and be very confident about what we know about these semiconductors. So as far as the switching speed is concerned, I can say the silicon is on the lower side. It cannot go for very high speeds. The silicon carbide can go to high speeds, and the gallium nitride can go to very high speeds. Then in terms of conduction losses, we will say that the silicon has high conduction losses, while both silicon carbide and gallium nitride have low losses. Then the switching loss is high as far as silicon is concerned, and it is low for silicon carbide, and in fact very low for gallium nitride. Now some of these things we will be able to relate with the analysis and calculations that we have done. Others would be following, we will be doing them as we will proceed with the course, as we will come to the respective portions regarding that. Then what about the thermal management part? Thermal management. So it is standard thermal management, whatever we know of. It is excellent management possible in silicon carbide. One of the reasons, as you know, is the high thermal conductivity. In case of gallium nitride, where we saw that the thermal conductivity was a bit less than silicon carbide, there it is a bit challenging, but things are improving there also. Challenging but progressing. And cost wise, okay, we can clearly see that the cost is lowest when you talk about silicon devices, semiconductor devices. You can say the cost is high when it comes to silicon carbide devices, and again a bit high for gallium nitride. So gallium nitride, the technology is still maturing, it is not matured, while in silicon carbide also you can say it is midway. It is not matured, but it is a little ahead of gallium nitride. And silicon, of course, is the most matured technology. Okay. Now, some of these things you understand and you are able to relate with whatever we have discussed so far and whatever analysis and equations we have seen, expressions we have seen. Some of them you are probably not able to relate. So, as I said, we will come to it. With time, you will understand many of these things. Okay, now let us move on to our first power device. Though we have studied various aspects of this power device, because we have studied PN junctions. So, I am talking about power diodes. Okay, so now let us see how typically a power diode structure would look like, and try to relate it with whatever I have been explaining to you in the last few lectures ever since we started semiconductor physics. So, if you recall, I am sure that it will not be difficult for you to very quickly identify this structure. So, let us say this is a full wafer on which the power device is fabricated. Now, this is the portion in which very heavy doping of the acceptor ions, acceptor atoms has been done. Okay. The typical doping density is about 10 raised to power 19 numbers per centimeter cube. Okay, so this I am talking about Na. Na, that is this density. And this length, typically you can assume, just to give you an idea, the technology is advancing, and I am just trying to give you an idea. Do not really take them to be very, very concrete and written on a stone or something, that we can't be different than what I say. Approximately 5 to 10 micrometer is the length of this particular region, which is a P plus type, heavily doped acceptor atoms. And you have an N minus layer. Now, I put plus to say heavily doped, I put a minus to say lightly doped, and I do not use any sign when I say it is moderately doped. So, please remember this notation. So, this is the N minus layer now, and this is the most important layer that we have introduced. We have seen some of these things, I have explained to you a few times earlier. We have seen some of this before, that this is to increase the voltage withstanding capability of the devices that you have to introduce in n-minus layer. And this is the philosophy which has been used throughout, and it's quite uniform across all the devices. Now, so therefore, if I say that this particular length, which is also called the depletion width, this length, it is important. It depends on what breakdown voltage you want to have this device bear across it, be able to take across it, and the doping of the donors. So, let me just denote it by D. So, basically what I am saying that this part, what I have drawn just now, this part, what I have drawn just now, is something that you need to design very specifically, because it's a power device. You will not find this particular portion when you are doing a PN junction or a small signal diode long back in your junior classes. And of course, then you have the this layer, which is the N plus layer. Sorry, I shouldn't be using the green one. I know that you will not be able to see it very well. Let me use the red only. N plus. Okay, and again, now these are donor atoms, and I have put a plus sign. So 10 raised to power 19 numbers of donor atoms per centimeter. Now, why I say something in farads per centimeter, why I say something in meters, blah blah blah, I am sure you all understand that that is to represent whatever numbers are getting involved, whatever analysis is getting involved, to simplify it, You write it, with least effort and with least complex looking expressions and numbers. So that is the idea. So people have learned with experience that typically if they write these in such dimensions using these kinds of units, then they are fairly okay, in terms of expressing the various units and quantities. So this is the structure, and typically this would be somewhere around 150 to 200 micrometer length, this length. And of course, though I didn't show here, you will have a metallic contact, and you will have a metallic contact here to make connection with the outside world, right, in your main circuit where you are using them. Now, before I come to this particular layer, this what I call as a drift layer, before I talk a little bit more on this drift layer, let me just remind you that we are talking about a power diode now. We are not talking about a small signal diode that we used to do before. Okay, so what is the main difference in terms of the IV characteristics of a power diode and a small signal diode, which is extremely low power small signal diode that we have seen before. The variation of the signals was very small. So let me just draw on this side. So this is the forward direction, and this is the negative direction. So as you can see, this is voltage and this is current, and here this current is extremely small. In fact, you can just put it on the axis directly. And now let us say you are increasing your voltage in the reverse direction. As you can see, we are on the left side. Okay. So a time comes, as you know, where this voltage, which is termed as the breakdown voltage, that your device would undergo a phenomenon which I described to you as impact ionization, and it will cause a breakdown, because there will be a big chain of flurry of charge carriers, electrons that will be generated one after the other, and we have briefly discussed that phenomenon. And so the current really goes very high at that time, and the device actually breaks down. here it is very important to understand that both your voltage and high current, both the voltage is high and the current is also high. So you can understand that this is really going to be a very high power event. It will actually generate a lot of heat, as you can understand. Now, what is happening on the right side? This needs a little bit of discussion. Now, in your small signal diode, what you have done is you used to show it like this. But what I would insist now that you actually show it like this. So, what do you see the difference? The difference is that in the earlier case, the small signal case, it is an exponential function, while it is becoming, so this one here, if I can just mark here as power diode, and if I can mark the other one as small signal diode, you can see that this blue one is more linear. Now, are we surprised about this? We are not surprised, because power diode, we have just seen, we have introduced a layer which is lightly doped, and though I did not write the concentration, I did not write the doping density, so on, that is something that I want to discuss with you, that is decided on the basis of what kind of voltage we want the device to withstand. Okay, we know that this is very lightly doped. So, it is not going to be 10 raised to the power 19, it is going to be some 10 raised to the power 13, 14 or 15, a very low value. So, obviously, when you have a layer of such a low doping density, you know that its resistance is going to be high, because the number of charge carriers per unit volume is very less. Okay. So, that is why in the forward direction, when my device is conducting, it is going to actually see a more ohmic type of relation that we see, from here you can see that is just give you this slope will give you 1 over r, actually I should say 1 over r, because I is on the y axis and V is on the x axis. So, 1 over r, it will give you that, and this r you can even write r on time resistance that will be actually exhibited by the device is this. Okay. Now, though I am saying that this is going to be linear, it is going to have more resistance, because it is going to have more resistance compared to a small signal diode, I will tell you after a few minutes that though it is more than a small signal diode, but it is not after all that much also, because of a very fortunate and a very nice thing that happens in such devices that we will study after some time, something called conductivity modulation. That is what we will see after a few minutes. So, for now this is the IV characteristic of a power diode. Okay. Now, let us come to the design of the drift layer. Okay. Let us come to the design of the drift layer. Okay. Now, do you remember we have written one expression a couple of lectures before, where I said, recall that we said the breakdown voltage VBD, we said is approximately, we actually wrote one expression which was epsilon into Na plus Nd, the acceptor and the donor atom density, into EBD square, which is nothing but the breakdown electric field square, divided by 2 times Q times Na times Nd. Okay. Now, we know that most of this drift layer, what we are saying, it is going to absorb the depletion layer. Whatever is that space charge is created, and if you see from our understanding also, We have taken a PN junction earlier where we had comparatively we had same doping density for both p type and the n type. But now what we are saying, we have a very high density for p type region and a very low density for n type region. So what will happen? You will find that from our understanding, your E field on the p side will probably be only, it will go up and steeply rise to the maximum value, but because this side here is n minus, on this side your ND is very less. Remember we said that the field, electric field is going to fall like this slowly, and we concluded that almost the entire space charge region would be accommodated in this layer because of this high doping and this the depletion layer, the space charge extend much into the p plus region. Okay. So, this you will have to remember and keep in mind. Now, if that is the case, can I not say that my ND is much less than NA? I can say that. I can say that. Just now we have seen highly doped and lightly doped, we have seen orders of magnitude difference. Okay. Now, when that is the case, can I not eliminate this ND as compared to NA? So, let me just do that. So, I eliminated ND and now only NA is there in the numerator. So, can I not cancel this NA with this NA now? So, if I do these things, then I will be able to write here my breakdown voltage expression. Okay, it will become epsilon EBD square divided by 2Q into ND. This is what that expression becomes. And now, if I substitute the standard values, if you see we have done that comparative analysis in the last lecture, from there also you will be able to make out, you will be able to see that if we are doing only for silicon right now, I have not gone to silicon carbide and gallium nitride. We will come to that after some time when we will do the further analysis and understanding. We will understand with the help of silicon semiconductor device first. Okay. So, I can put the value of Q, I can put the value of epsilon, whatever is it for silicon, and I can put the value of EBD, whatever is there for silicon, and you can see that your VBD you can write as 1.3 into 10 raised to power 17 divided by ND. Fine? Fine. So, there is no problem as far, I have just put the standard values, whatever is there, whatever the other variables or parameters are there in this equation which have known values, defined values, we have put that and we got this. It's a very nice compact equation, much better than something like this what we do. Now, for a given VBD, I can select what should be my ND, the donor density, right? And if I dope my N minus layer with this doping density, that number, I use that particular number for doping, then I can say that now I can apply a reverse voltage as long as it is at or below that, there is no problem to the device. At least ideally I can say this, right? Now, like I have done this, if you remember that in the beginning when I was just starting with the junction and I was mentioning to you the use of the Poisson's equation to get the electric field and the contact potential and so on, remember that time? We have seen at that time that our field profile was something like this. where I said this number is minus xp and this number is xn, because we said this is p type and this is n type, and we said we have plus here and minus immobile charges here on this side. That's what we had done, and this we had also concluded that this will be the peak value, which will be at the metallurgical junction. Now, considering that the situation is changed a bit, okay, and this minus xp has actually, you can assume that it is lying on 0 almost, because actually the way your field is going to vary is like this, not like this, it is actually going to be like this, and majority of this will be like this. So, it will be, if I magnify it, it will be something like this, right. Now, how do I find the area of a triangle like this? We know that it is nothing but half into base into the altitude. And what is the base? If I say that my entire depletion width is now accommodated in the n minus zone only, can I not say this is approximately, this particular thing is equal to WD? And can I not say this peak value or the height of this triangle is E max? So, can't I do half into WD into E max to get the voltage bearing capability? That is the integration, and the integration is nothing but the area of this. So, if I do that, I can show very simply, if I do this analysis, I can very simply show that this WBD, if I consider this to be the limiting case, I can show that this will be equal to 2 times VBD divided by EBD. It's just an extension of what I just told you, just the same thing I have written, fine. Now, using this and this particular equation, I can find out that for a given ND, what ND I have, for a given VBD, what ND I have chosen, and once I know that, I can use that value here, and this is maximum value is fixed. I can find out what should be the width of that layer. You get the point, what I am saying? First, we have used this expression to get to a relation between the maximum voltage handling capacity, breakdown voltage, and the ND, the doping density. Okay, so we fixed those things, and then having done that, now using this relation, I am now finding what is the depletion width that is required to accommodate that particular voltage. So that's all we have done. There is nothing very big about it. So the point here is that you must have at least this much of width. So whatever drift layer width you are putting in that diagram, which I have done a few minutes ago, that width must be greater than this width, what you are getting here theoretically. So that is the point I am trying to make. Now, it turns out that for silicon devices, this is a very reasonably high value. So obviously, in that diagram where you have some 200 micrometer of N plus layer, you have some 20 or 10 micrometer of P plus layer, and this particular layer that we are just now calculating, the drift layer N minus layer, it is also turning out to be pretty large for silicon. So the device will be bigger. You get the point what I am saying? Now, in a silicon carbide and a gallium nitride device, you will find that you can actually have a smaller size of this drift layer. You can have this W smaller, much smaller WD compared to what you are having in silicon. So please note the difference at this point itself. So difference with silicon carbide and gallium nitride is quite obvious. Okay. Now, it is not that people have not tried to reduce the width of the depletion layer or the drift layer as it is called in silicon devices, silicon diodes and transistors. They have tried. Now, when you have the applied voltage which causes the depletion layer to extend all the way up to the N plus layer. So, what I am trying to say is that let us say this is my junction. This is my junction. What I am saying, there is an N layer here, N minus layer here, and there is, sorry, I will just draw it like this, N plus here and P plus here, like that. What I am saying, that your depletion layer, one is that during the reverse bias, it actually gets like this and does not go all the way up to this boundary. So, this is the depletion layer. For still higher voltage, this can go like this. For still higher voltage, it can go like this. Now, when this happens, when this case happens, let me put a star there. This is called a punch through diode, because the expanding depletion layer has punched through the entire drift layer and it has reached on the borders of N plus. So, this particular thing is called the punched through diode or PN junction, whatever you want to call it. Okay, now people have, as I said, they have tried to reduce the width of this drift layer, because everybody tries to save cost, they try to also make the device more compact, if I can probably manage. So, there was one such possibility or one such technique which was proposed, which I will just explain to you with the help of a diagram. Just one such thing we will see. There are many such attempts. We will just see one because of for the sake of completeness. Okay. Now, look at this diagram. And let us say that this is the boundary or the junction, and this one here is the other one, junction, and this is the drift layer, what I am showing you in the middle. This is the drift layer. This one here is N minus region, sorry, N plus region. This here is N minus region, this here is P plus region. Now, let us see how the depletion layer has spread during one reverse bias operation. Let us say it has spread like this. So, what it shows basically, I will just explain to you, give me a minute. You see, first of all, it is a punch through case, as you can see, right. Why? Because you can see that it is reaching all the way up to the, the end where the N plus is starting. So, this is a punch through condition that we all understand. Now, let me call this particular region, I can present it to you as a combination of a rectangular and a triangle region. This one here, let us call this as E2, this particular height, and let us call this here, this particular one, as E1. Okay. Now, if this is x, by now you all understand very well that this is x axis. Okay. So, you know that if I integrate in this area that which I have shown you. If I integrate, so I get this area basically. Okay, that will give me the voltage, right? So I just say that let us say this part here is able to bear a voltage V1 and this part here is able to bear a voltage V2. Now, because the fact is that because this particular layer which has spreaded all the way up to the n plus end, I can say that it is that drift layer, and I can actually represent it by this well known relation that you have already seen before. I will just write here E1 is equal to, I can say Q N D into WD divided by epsilon. Do you remember this particular expression? We have done it before. Remember, I wrote it in the beginning when we started with the Poisson equation. Then I said take a one-dimensional Poisson equation, get the value. So we even have done the integration and derivatives at that time. So we have got this. So this is that expression. So E1 is actually given by this expression. Question? Is there any question? Okay, sorry, I thought there is some question. So that is one. Now, if this is the electric field E1 associated with this particular region, I can say V1. You know that how to get V1 if the E1 is given, you know that, right? So that actually turns out, again we have an expression for it. If you will look back into your notes, you will find that it will be Q ND WD square divided by 2 epsilon. That is what it will be. If you see your notes, whatever we have seen before, or if you see the previous lectures, you will find that this is what we have got. Now similarly, so this was for the triangle, that portion. For the rectangular portion, can I not write V2 is equal to E2 into WD directly? Can I not do that directly? Because I just need this area. This is rectangle. E2 into whatever is the width, WD. Fine. So I can write this V2 like this. Now you see, when the punch through has occurred, you know, we are already at this point. It must be the point where your breakdown electric field exists. So this point here should correspond to, at that time, EBD. Breakthrough is about to occur, or has not occurred but about to occur, or has just occurred. We are just at that critical limiting point. So if that is the case, can I not say that this entire, this plus this E1 plus E2 is equal to E breakdown? I can do that. And similarly, I can also say that these two voltages will correspond to, if the breakdown we are at that limiting point, we will say VBD, okay, that will be equal to V1 plus V2, isn't it? That is all. So what are we trying to do? Please don't get mixed up. We are just trying to say that we have accepted a punch through situation. See, what is my worry when I increase the length of my drift region? What is my psychology? I don't want, in the first place, that punch through should occur. I don't want the diode's depletion layer extending all the way up to the n plus point junction. I don't want that. That is what I want, and that is the reason I make it bigger or lengthier, longer, and avoid punch through. I am saying now, because of this long length, I am ending up with a big device. Is it not possible to let this punch through happen as long as it does not destroy the device? Let it be there. can I not live with it? Because I can now reduce the size of my device. So that is what we are trying to do. Okay, so if you understand this point, then you allow me to write down further that your VBD, simple manipulation, mathematical manipulation of these equations, you can say that it actually will turn out to be EBD into WD, okay, minus QNA into, QND, not NA, QND, donor, T into WD square divided by 2 epsilon. Okay, and basically what I have done is, here you can check that V2 I have just substituted equal to this EBD minus E1 into WD. If you see the previous expressions that we have written, I have just done a simple manipulation and I got this expression. Okay, so basically I have not changed as far as my target of VBD is concerned. I have not changed anything. But what you see from here, that can I make an attempt to reduce the value of WD from here? Is there a way I can say? So can I say now further down, can I say VBD equal to WD into EBD, or WD is equal to VBD divided by EBD. If you remember what we have seen the previous analysis, when we did not do any of these things, when I just took a simple case, it actually turned out that this was 2 times this value. Okay, we actually got 2 VBD by EBD, this expression by EBD. We had actually got this expression. Okay, now what we are getting? We are getting this expression. Okay, so what does it show? That by reducing the value, so basically, if I make the doping density in the drift region to be much smaller, I can write this. So basically, you can just write here, if ND is made very small, then I can just simply get this thing, this particular thing, but this will become very small. That's the point. So you can reduce the doping density much lower than what we actually obtained in the initial analysis, previous one, okay, where I wrote, if you remember this expression, 1.3 into 10 to the power 17 by all those, that analysis we have done. So there I have actually, we have written this expression we have seen. So basically what we are saying is that if it allows you, your design allows you to reduce the density of your doping atoms, Nd, then you can actually, for the same breakdown voltage, okay, you can get your device the length of the device or the drift layer to be reduced drastically. That's what you will get. So basically by reducing Nd, but it has to be done much beyond the permissible limit of punch through condition. That's what we have assumed in the previous case. Okay, right? But the point is that you have to understand that if I am reducing Nd to achieve this, what am I doing? I am actually increasing the resistance. I am basically increasing the on resistance of the device. So it will actually cause more losses. So my device would be compact, but I have increased the losses. When we fabricate the power device, so n plus, n minus. Now typically how this is done? So this is, let's say, the top of the wafer, and what people will do, people who are experts at actually designing and fabricating these kinds of devices, what they will do, they will mask this particular portion and they will mask this particular portion, and they will bombard with acceptor atoms. They will try to do implantation of the acceptor atoms. It actually through this window. This is insulator, typically SiO2. Okay, silicon oxide layer. It is actually an insulator, dielectric. Okay, and you might have heard about this when you were doing MOSFETs. That insulation layer is actually achieved through an SiO2. So as you can see from here, you are inserting several of these acceptor atoms. And why we are doing it? Because my aim is, which I have not shown deliberately, my aim is because that I want to create a P plus here. Then only I will be able to get my power diode, right? So wafer, okay, this N plus has been grown, N minus has been grown probably, and now P plus is being grown. And what you do is, because you want to have this only limited to this region, you actually mask the other region. You don't want the acceptor items to actually go and bombard those areas. You just want them to go through this window. But now the problem is that because of these fabrication techniques, you will not get those nice boundaries of the junctions. So what we do usually when we are doing analysis, we are saying this is my device, this is the junction J1, this is P plus, this is the junction J2, this is N minus, this is N plus. See, very nicely I have drawn these boundaries. Actually, because of the fabrication difficulty, this is not possible. We are actually operating at a very small size, very low size. So what happens is basically that when you actually try to implant these here, they just don't go below and settle like this. What happens is that they actually spread out. So what will happen is, typically, if this is my SiO2 mask and I am doing the bombarding from this side, you will find that this will also go in this direction through diffusion. It's not that it will just be here. It will also turn around these corners and go to this right and left and all that. So basically what will happen is that it will deposit itself in this way, not like a nice square or rectangle which I have been showing you. Now the problem is that now this is your P plus layer and here is your N minus layer, and this entire thing is where your depletion layer is going to fit. When you are applying a negative voltage, reverse voltage across the device, the reverse bias, during reverse bias, this particular layer will spread and it will get accumulated here. So basically now you have to understand that during that time it is nothing but a capacitor. It is a capacitor. With, as you know, we have seen positives on this side and negatives on the P side. You know that. So the field lines, they will try to run from the plus to negative side. Now this negative side, if it is like this, then you will agree with me that these lines cannot be perfectly smooth and equidistant. They would have to probably, because of this curvature, these lines will get crowded at some places while they will be relaxed and spaced out at other, in other regions. So what will happen? You have a concentration of electric field lines in certain areas of this curvature formed because of this process. So it's like, at that particular point, it will cause some sort of a hot spot. Too much of concentration of the field. And it can actually kill your device even during the time of fabrication. So people actually follow different methods for doing this. One of them is the use of field plates. So there are various methods of avoiding this. One is the use of field plates, and the other is the use of guard rings. And so on, and there are many such possibilities are there which people have discussed, but for you this is enough. Now I will just briefly tell you about what is the method that involves the use of field plates and how the device is protected. I will just explain that to you. So basically what they do is, let me just take a section of what I showed you. So they have, typically, so this is that P plus which has been formed. Now what they do, they put metal plates, very thin layer of metal, and that will look something like this. Like this, metal layer they have put. Now wherever this particular terminal P plus is connected, it is the anode part, right? Anode A, I mentioned to you, right? Now because it is a reverse bias condition, typically it will be either 0 volt or it will be some negative volts. Reverse bias, you have put a lower potential on the positive anode side. The usual reverse bias and the forward bias conditions, I am talking about that. You connect these to the same potential, these metals. Now when you have this N minus layer which is trying to have these field lines run from the positive side or positive charge layer or positive plate of this onto this, it will not rush for this particular edge. It will, because this will be more uniform now, these fields will not be so crowded. They will go here, they will go here, they will go here, like that. They will be spread out. They will not be, if this was not there, all of them will try to go here, like this. And they will crowd and cause hotspots. So this is one way where people have used field plates to try to reduce this crowding of the field lines. So this problem is called crowding of the field lines and is an important concept to know in the power device area. It is more significant in power device area. In small signal devices, you don't have this kind of voltage and fields and so on, which will cause this kind of a problem. They have their own other issues to deal with. Now, this is the situation. This is a power diode. We are just showing a cross section of the semiconductor that makes up a power diode. This is P plus, N plus, N minus. Okay, and let us say that this is under forward biased conditions. So this is positive and this is negative. Now when the current will flow in this device, so let us say there is a current IF during the forward conduction mode, IF is flowing through the device. So obviously this current is going to flow like this, and while flowing like this, it is going to see a very big region which does not have any charge carriers, or which does not have many charge carriers. So this guy here is high resistance region. So though this particular picture and what we have even seen before, we talked about the ohmic resistance displayed by these devices due to the presence of the n minus layer. Does it really cause a problem? That is what we are trying to say. So now if you see this carefully, what is happening is that this guy is positive and it has got holes. So let's draw some holes here. And now these are electrons. I should have probably shown the other color, interchange the colors for the two. Alright. Now let's say that because of the flow of this current, isn't it that these holes are trying to flow across like this? During the forward bias, the holes, they try to diffuse and go on to the n side, and then out of the terminal they go towards the negative terminal, and on electrons from this side, they actually come on this side because the junction potential, contact potential has been reduced by the applied voltage. They are just trying to go here, and they actually, those electrons, they emerge from here and they go to the negative, positive terminal of this. This is what we have seen before. Now when these electrons are trying to go here though, they do try to look for some electrons for recombination. There would be some electrons and there will be some recombinations taking place. But when there is a large current flowing this way, do you agree with me that there would be an accumulation of a positive charge here, because there are not enough electrons in the n minus layer to annul this positive charge which is coming from this side? So isn't it true that this particular region, the central region, this one, it will start appearing a bit positive if you try to look from this side? You get my point what I am saying? Your holes are trying to flow across the junction because that is the job, that is the operation of your PN junction. Please don't think that we are talking about anything which is new or very big. This is what we have seen. In a forward biased PN junction, this is what will happen. So they try to go here, but because the electrons here are very less, this region will have some sort of a positive appearance, isn't it? It will become positive compared to this one. Now when that happens, electrons from this region, this n plus region, they get attracted into this region dynamically. So even though the doping here was only 10 raised to power 14 and you were not expecting many charge carriers, because of this phenomenon that you have the holes injecting from here and the electrons injecting from this side to this side, you have this particular layer becoming rich in charge carriers as well. So now if any current is flowing in this device, it will see not a very large resistance in this drift region. There is anyway not such a large resistance in these regions because they are thickly, highly doped. This particular region was the only problem. So now with this phenomenon, which is called the phenomenon of double injection. So this is actually called the phenomenon of double injection. That you have a flooding of carriers, and if you want to represent the combination of holes going from the left to right and electrons coming from right to left, you will always have some average number okay, and that average number, let us say you call that as an NA, average, NAV, let us call it that. So, there will be a sizable NAV population here during this time, and this will reduce the resistance, and this is actually going to cause the modulation of the conductivity, which was previously thought to be less. Because of this phenomenon which is happening, the phenomenon of double injection, you have conductivity modulation. So, in spite of the fact that device is bipolar, it has both electrons and holes responsible for the current, it is a bipolar device. Because of this particular thing, you have the storage of this charge, space charge in this drift layer to absorb the reverse bias, and which causes problems to us when we are trying to switch the device, because it cannot go from on to off or off to on till this problem, these particular charges either stored or taken off from there, depending on whether you are switching or you are switching on or whether you are switching off. It causes delay in switching. In bipolar devices, this is called reverse recovery problem. So, that is the next topic what I want to do with you. I want to explain to you the switching waveforms, and I want to explain to you what we mean by reverse recovery process or reverse recovery phenomenon observed in bipolar devices. Now, reverse recovery phenomenon is not observed in majority devices like MOSFETs. You do not have there one device which is having current because of both holes and electrons. You have a device which is conducting only either because of electrons or because of holes. So, you have a P-type MOSFET and you have an N-type MOSFET. Remember? That is the reason. So, they do not have these problems of stored charges as we have seen, and the reverse recovery issue that we will see now will not be a problem there. But you will find that something happens and there is no conductivity modulation taking place in these majority devices, something which is happening in bipolar devices. So, their losses are low. Your power BJT, your power diodes, they are less lossy compared to majority devices. A very interesting and important observation. So, always remember the phenomenon of double injection in these bipolar devices. Your power diode that we have seen is a bipolar device. Now, it does not matter whether it is made up of silicon, does not matter whether it is made up of silicon carbide, does not matter whether it is made up of gallium nitride or gallium arsenide, I do not know, whatever is possible. Same thing would hold everywhere, but the extent, values will be different, because they have inherently different properties. That is what is the point. So, double injection phenomenon, where you have injection of electrons and holes from the two sides into the drift layer region, causing multiplication, or I should say modulation of the conductivity of the device. So, if somebody wants to really see how the profile of the charge carriers would really appear during the time when you are switching off a device, basically, is that you must have switching on a device, not switching off, switching on a device. You must have a build up of these charge carriers in the drift layer, basically. So, typically you will see these kinds of diagrams which are very popular with people. So, this is that P plus N minus junction, and this is that N minus N plus junction, and you will actually find that during the on process, this is going to be roughly the profile of these charge carriers which I just mentioned to you, the ones which are getting injected from here and injected. The average of this is what I was saying, you can take as some, I think I wrote some NCM or something for that. So, you can actually assume this to be an average value of the charge carriers which are there. And of course, on this side you will have the usual minority carrier profile, your electrons on this side, which will be going down and down, 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 down as we are going away from the junction, because they will not be able to go through the, the herds of holes which are present on this side. They will get mixed up, they will get basically, they will collide, they will recombine, and then they will go. Similarly, here these are holes. They are trying, they are not able to go very far before they are caught. So you can see that their profile also is decreasing, gradually falling. And there are standard formulas, standard equations which people have now been able to develop, which clearly show how these profiles they vary. So I will stop. Actually, there is no time, not much time for me to do the switching characteristics. So thank you very much for your attention. Thank you very much.